And here,
is that the Newman-Penrose thing?
It does use the coordinate
source.
I don't understand that from most of my get a hang of it.
But I don't know.
it comes from the sky.
Is it slides?
He's got to do slides.
There it is.
Yeah.
Oh, did you? I just noticed. Now,
Sure, we
both
can
of
do
the-
these slides and
if you look at the
Two what?
two
the blurbs on the back.
That's pretty good.
That's actually pretty good. That's like pretty good enough.
Correction.
Yeah, sure. It was
First it was
one possibility to
one Nobel Prize winner. Yeah.
Tonight is easier than just teaching. Okay,
We usually do tonight.
let me start.
Oh, do you want?
I actually have.
You have one?
As well.
Okay. Emil, as someone usually on the Zoom, do you think this is readable enough if they just see the video of the slides? Should be okay. Typically, let's show things on that.
Yeah, exactly. I'll end up writing on the blackboard and stuff.
I think that's good. Because if you're going to also write on the blackboard,
Yeah.
then we could choose.
Yeah.
Yes, it'll be writing out over here.
Yeah, exactly.
That's expensive.
Yeah. Mine are to take Moscow.
Yes. We are recording.
Yeah, I got a notification of the call.
Just check the feedback.
So it is
Yeah.
I just do it when
And
I
it's being
get
recorded.
stuck.
okay. Will you go to the cloud? You should go automatically to the cloud.
To the cloud.
Yeah, I got the class.
Oh.
What was the last talk? I'm sorry. No, that one we just put on the general thing, right?
No, we did that as a private.
This morning I was stuck on
Good.
something.
That's just, it's up on the, it's on the
Yeah.
YouTube channel.
Yeah, so is that group to.
Next one. Okay, I think we can start if you're ready. Okay, everyone, so today we have the pleasure of having Geoff Pennington, sort of coming from Berkeley / IAS, to tell us about some work he's been doing with Chris Ackers. So Geoff, please take it away.
Okay, awesome. So thanks so much for inviting me here to talk. So yeah, this paper is entirely motivated. The entire reason to care about it is ADS-CFT, basically quantum gravity. But the actual content of the paper is essentially entirely finite dimensional quantum systems and channels and so on. So very sort of quantum information-y in style. So makes it a bit of a challenge to present because the high energy theory people, the people who might be interested in hearing about it, but there's a sort of lot of background stuff. So I will do my best to make it as clear as possible, but please shout and interrupt with as many questions as possible to try and make this interactive and hopefully get both motivation and the technical content across. Okay. So the talk's called quantum minimal surfaces from quantum error correction. So let's just start with quantum minimal surfaces. What are they? Why should you care? Well, there was a formula for if we have ADS CFT and we look at subregion of the boundary of the CFT, there's a formula for its entropy. Okay, there's various versions of this formula. It's very famous. Started with the Tachinagi formula. The formula I've given here includes quantum corrections, but it's only valid for static states. And it's just that you consider all possible bulk regions, little b, and then minimize over all those regions the sum of area of the boundary of that region divided by 4 times Newton's constant plus the bulk entropy of that region. Okay, so this is called the quantum minimal surface, whatever minimizes this. And the minimal value, this is called the generalized entropy, the formula in the brackets. The minimal generalized entropy gives us the boundary entropy S big B. Okay, so as I said, this is really just valid for static states. For general time-dependent states, you have to worry about what slice you should be using when you do this minimization, right? So implicitly, I'm minimizing here within the static slice. But if you don't have some time reflection symmetry, at least some static slicing of the bulk, it's not clear what slice you should use. And there's a simple answer to that, which is you should sort of try applying this formula in all possible slices, and then take the answer take the slice that gives you the largest S big B. Okay, so you maximize this minimum over all possible slices. So that's the right prescription. It's called the version I just gave is called the max-min prescription, but it's equivalent to what's called the QES prescription, maybe more famous. But that part, that's the maximizing over time slices, is going to be beyond the scope of this paper. Okay, so you can either think of this talk as just about static states, nothing else, or you can think about it as like explaining this min part, but not trying to explain the max part in general cases. Okay, so we're just going to focus on this simple formula. Okay, so for the rest of this talk, I'm going to set 4g equal to 1 because there's no reason not to, and get to 9. Okay, so there's a closely related idea to this formula for the entropy, which is this idea of entanglement wedge reconstruction. So what does that say? It says that if we consider the same B that we found before by minimizing generalized entropy, then there's a certain sense in which the reduced density matrix of the boundary CFT on big B encodes that bulk region little b. Okay, that any information in the bulk here is in an appropriate sense also available in big B. This can be precisely understood, and I'll talk more about how it should be precisely understood later in terms of quantum error correction. Okay, so now we've had the 2 ingredients of this talk, quantum minimal surfaces and quantum error correction, starting to show up. But for the moment, I'm just going to leave it pretty woolly as a vague statement that encodes that region. So if we have some pure bulk states and hence pure CFT state, we can also do the same process for the complementary boundary region, big B bar. Okay, but just because the entropy of two complementary regions in a pure state is the same, and also the boundary between 2 regions has the same area for both sides, then the minimization for big B bar will end up giving the complement region, little b bar, to the region that big B encodes. Okay, so the 2 complementary boundary regions encode 2 complementary bulk regions. This is an idea known as complementary reconstruction, but it's just a fact about that formula for finding the entanglement wedge, for finding the quantum minimal surface when applied to pure bulk states. I'll talk more about mixed states later. Okay. Okay, so in 2016, Daniel Harlow put out a very beautiful and really sort of groundbreaking paper. And what he did in this paper is he just said, forget about gravity. Let's just assume we have some quantum error correcting code, and we're going to assume it's a complementary quantum error correcting code that has complementary recovery, that has this notion of complementary subsystems. In this case, there'll be logical subsystems encoded in our physical systems. That base some version, where complementary logical subsystems are encoded in complementary physical subsystems. Okay, again, I'll describe the formulas in more detail in a moment. I just want to lay out the sort of vision for how his paper worked for now. Okay, and he showed that any such code obeys a formula, and it's a formula that looks very much like the one I showed on the first slide for quantum minimal surfaces. It says that the sort of boundary entropy of your CFT state V here is sort of a map from your bulk state to your boundary state, is just equal to the bulk entropy in the region little b that is encoded in big B, plus some extra term that in fact is just a constant that I've called A. Okay, and I've called it A because it's analogous to area. Yeah.
Do any of the codes that one would learn about when worrying about, basic quantum computation, like CSS codes, toric codes, or et cetera, do any of those have complementary recovery?
Yes, they do in a sort of trivial sense. Yeah, I'll talk more about this later. But the most basic quantum error correcting codes you'll learn about in the first class in quantum information or whatever. All the information, all the logical information, the analog of the bulk, is all encoded in the equivalent to big B. So it's like complementary recovery in the sense that everything is encoded in big B and nothing is encoded in big B bar.
Does that make the geometry trivial then?
Yeah, it means that sort of. So I'll talk about the sense in which we have a geometry at this point, and it's already pretty trivial, but in that case, it's sort of arguably even more trivial. That the entanglement wedge of big B contains like the entire bulk.
So is that the substatement that it's not possible to split the code into sort of two pieces?
Yeah, so it's just a different sort. I'll talk about this again later, but it's a generalization of ordinary quantum error correction called subsystem quantum error correction, where you actually have different subsystems. You only have one subsystem of the bulk encoded in big B. It's the relevant quantum error correction for quantum gravity, but it's not the one that you learn in like the first time you see a quantum error correction code. But I'll show all the different versions of quantum error correction one after another later in the talk. So yeah.
And in this formula, what we don't have geometry to sort of guide us. What do you mean by big B and little b?
Yeah, good. So maybe I'll just draw it now already. So what we really have here is we have two logical subsystems that are getting encoded, little b and little b bar. They're getting encoded via some isometry B, and then they're getting encoded into two physical subsystems, big B and big B bar. Okay, and then you like the condition of having complementary recovery is that little b gets encoded in big B and little b bar gets encoded in big B bar. Okay. I'll explain in detail, definition of all of these things later. But for now, I just want to sort of look at this formula and make a couple of comments on it. Okay, so this sort of looks an awful lot like what we just saw in the first slide. And we got it from some quantum error correcting code that a priori had nothing to do with gravity, that had no notion of geometry or anything like that. Okay, and actually there's the converse statement is also true. If an equation like this holds for some area A, for all states in your code space, for all states on little b and little b bar, then you actually also have complementary recovery. So there's an equivalence between sort of having this geometrical like formula and having this information theoretic reconstruction of different things in different regions. Okay, so this is very exciting for a couple of reasons. One of them is that we're getting this sort of central feature of gravity. Like arguably these sort of formulas are one of the most important formulas in ADS-CFT. I think I would maybe argue possibly the most important, though people could obviously disagree with that. We're actually getting it just from quantum error correction, just from information theoretic principles without needing any sort of super Yang-Mills or anything like that. So it's sort of, in a very flowery, possibly over the top interpretation, you could say that any quantum error correcting code with these properties having some sort of emergent bulk geometry. Now, what do I mean by emergent bulk geometry? I mean, there's some constant A here that I'm calling an area of a single surface. That's actually the entirety of what I mean by a bulk geometry at this point. So it's very reasonable to say it's not much of a bulk geometry, but it's at least something that has the flavor of the geometry. Yep.
Is there some way to interpret this area in terms of like the geometry of state space?
Geometry of state space. You mean like the geometry of the Hilbert space or something? So it's related to the entanglement structure. It's related to the entanglement structure of the code. basically this is saying that this state V of psi has two sources of entanglement. One of them is coming from like bulk entanglement, and one of them is coming from just entanglement like from the code itself. And that's what that area term is corresponding to. But it's really just a number at this point. It's just like one number, and you know, we shouldn't get too ambitious about how we interpret it, that you know, there's a flavor of something along these lines. Okay. So great. Beautiful paper by Daniel. It's great. One of my favorite papers. I encourage you to read it. It's beautifully presented. So what else do we have to do? Because honestly, if I gave the like one sentence summary of my paper with Chris, it would be almost the same one sentence summary you could have given to Daniel's paper in 2016. Okay, so in what way have we done more? In what way is the 5-sentence summary of our paper different from the 5-sentence summary of Daniel's? Well, one thing is that in Daniel's formula on the previous slide, we had no minimization over little b, right? Because there's just one little b here, and that's just the one that gives the answer.
Can I ask just one more question about that formula? So I know this is an analogy to the geometrical situation, but in this quantum error correcting code situation, what does A depend on? Does
It depends on
and psi? But
no,
it's true
it's very important that it does not depend on psi, right? Because we want to consider a set of bulk states that all have sort of the same geometry.
The
right?
two of the terms depend on psi, right? You have explicit.
Yeah. So let me just go back.
The difference between S capital B
Yeah.
is independent.
It's independent of psi. It depends only on this isometry V that sort of defines the code. So it depends on the code, but it does not depend on the state. Yeah.
But that's true for a subclass of states or for all states?
It's true for all states psi, but the state psi is like your input state here, right? It's like your bulk state. So it's you know, it's true for the states within your code, but that's not all states on this larger Hilbert space up here. Okay, V is an isometry, it's not a unit. Cool. Okay. So the reason there's no minimization over little b in Daniel's formula is that he's basically assuming in his theorem that the same little b applies for all states in the code space. Okay, so you know, when he assumes complementary recovery, he assumes that there's just some fixed little b that gets encoded in here that does not depend on the state psi he's considering. And hence also the formula he gets of area plus entropy of little b is just for that fixed little b. And so there's no reason to minimize over little b's because there's basically only one.
Sorry, doesn't that mean the answer to Jeff's question is that all three terms were independent of psi?
No, because we have S of little b is fixed. But the entropy of little b depends on psi. Right, we had, yeah. One entropy is equal to an area plus another entropy, and both the entropies do depend on psi, but the regions little b we're computing with do not depend on psi. Okay, so you know, this is true in certain special cases in gravity. It's true you have some small code space of states with a fixed area and you take the semi-classical limit. But in general, it's not true, and it's not true in very important ways. Okay, and so I've got an example here, which is sort of possibly the original example of this came from a paper I wrote with Patrick Hayden back in 2018. And the way it works is we consider a code space that consists of black holes sitting in the center of ADS, and then we look at our region B being sort of part of the boundary, a bit more than half of the boundary. Okay, so now we can consider two different states within this code space. We can consider the black hole being in some fixed microstate. Okay, in that case, when we want to minimize over area plus entropy, then we find that the sort of corresponding little b contains everything up to this minimal area surface behind the black hole. Okay, because the big B consists of more than half the boundary. So this thing has smaller area than this thing. There's no bulk entropy sitting anywhere around. So this whole big region, including the black hole, ends up being in the entanglement wedge, ends up being the quantum minimal surface is gamma 2. But we can also consider another state. We consider the state where the black hole is in some highly mixed state, say a thermal state or something like that. Okay, in that case, the generalized entropy of this surface over here gets a giant contribution from the bulk entropy of this black hole, right? From the Bekenstein-Hawking entropy of that black hole. If we've chosen our parameters appropriately, that will actually end up being bigger than just the area of this surface. And for the area of this surface, then little b excludes the black hole, so we don't get that big entropy contribution.
I think, okay, sorry. I was just saying that it's just not obvious to me that the surface can't cross the black hole. Is that some GR theorem that?
Yeah, let's assume, well, let's assume that there's at least a long wormhole behind this black hole, that there's not some sort of short geometry that ends, short wormhole ending within the black hole. For a thermal state, there's some very large amount of entropy in there, and you sort of can't exclude that entropy. Yeah. But let's just treat this black hole as just a source of entropy and not worry about geometry behind the horizon. I could say more words to justify doing that, but I think it would be sort of a distraction. Okay, so if you prefer, you can actually, with a very slightly different setup, you can replace a black hole by just a load of relatively high temperature dust or something that just has some entropy. Okay, so that's one example. That's maybe the original example. It's a much more important example, in fact, which is evaporating black holes after the page time. So this is what happens in all the stuff from 2019 with replica wormholes and islands and so on. But what happens there is that if I have a state where the Hawking radiation is entangled with the interior of the black hole, that changes the entanglement wedge. Okay, it makes the entanglement wedge contain most of the black hole interior, because that makes you avoid having a large entropy contribution from the entanglement entropy of the Hawking, the semi-classical entanglement entropy of the Hawking. On the other hand, if I just have some state where the Hawking radiation is in a pure state and the interior is in some other pure state, there's no reason to have that happen. The entanglement wedge of the Hawking radiation does not contain the interior of the black hole. Okay, so you measure the Hawking radiation, you get some answer. Then after you do that measurement, it will no longer encode the interior. So this is something we should care about. We need to allow this sort of bulk entropy contribution to change, which little b minimizes the generalized entropy formula. We need to allow like different states to have different entanglement wedges. Okay, so let me make one final comment before I sort of lay out the vision of the paper in full, which is what has now happened to complementary recovery in these cases. So let's consider that highly mixed black hole state where say this is in a thermal state sitting in the middle. As I said before, big B only encodes this region little b that doesn't include the black hole. Okay, because the black hole's entropy is too big, it makes the generalized entropy of this thing too big. But we can also look at big B bar. And again, the entanglement wedge of big B bar will only contain little b bar. It won't contain the black hole, because again, it doesn't want to have that source of entropy. So it will just be the surface gamma 2. Okay, so we now seemingly don't have complementary recovery because we have this mixed state. So there's this gap, this region in the middle, little b prime, that is neither in the entanglement wedge of big B nor in the entanglement wedge of big B bar. However, there's a general sort of philosophy in quantum information that I think is very important, which is that you should never actually think about mixed states. Whenever you have a mixed state, you should always think of it as there's some purification of that state and you're just looking at some reduced state on some subsystem. So let's imagine we did that. Let's consider some purification, get psi, of this mixed state with the black hole and thermal state. Okay, so we purified the black hole just by some arbitrary auxiliary reference system, R bar. Now let's consider doing the minimizing generalized entropy for not just B bar, but also this reference system, R bar. When you have this reference system, you need to use a slight variation of the formula we had before, but the only thing really that changes is that R bar gets included in this bulk entropy, S of B and R bar rather than just S of B. Again, this variation was originally introduced in my paper with Patrick in 2018, but it's also vital for the evaporating black hole calculations, right? This is the formula that if we apply it to the Hawking radiation gives like an island. Hawking radiation is an auxiliary reference system. Okay, so in this case, you can actually check that now the bulk state is also getting purified by this reference system R, and so this minimizing over B tilde for B bar and R bar will give us the complement of minimizing over little b for big B. So now, in fact, we find that B bar and R bar encodes not just little b bar, but also little b prime. Gets all the stuff that isn't encoded in big B. Okay, this is again just because now we're considering, this is the same as the entropy of the complement of B tilde. So now we're considering pure states in the bulk, we get that complement.
How are we guaranteed that whatever we're adding to the system to purify it splits in the same way as B and B bar split from the total?
Oh, that's a choice. So so we could also consider what's encoded with big B plus part of the purification. And in fact, later in the paper, that's, full generality, that's what you want to do. But to get some statement of complementarity, what we want to say is if I split the boundary system into any two halves, then the bulk will also get split into two halves, right? And the everything not encoded in one will be encoded in the other. So what I'm saying is if the two halves we split into our big B and everything else, namely big B bar and R bar, then we do get complementary recovery. Like everything is either encoded in big B or it's encoded in the.
I think he was asking a slightly different question.
Sorry.
So there's an R bar on the left-hand side of the equation, and there's an R on the right-hand side.
Yeah, sorry, that's a typo.
That's it.
Sorry, I apologize. Yeah, that there is a virtual bar on top of that R. Yeah, sorry about that. Okay, so the lesson of all of that, there was a lot of words, but the point is, as long as we think about the purifications of mixed states, then we still have complementary recovery. Everything is either encoded in big B or it's all the stuff in the boundary that purifies big B. Okay, it's just the mixed states weren't the right thing to think about.
Sorry, what is B tilde, little b tilde?
Oh, that was just, I didn't want to use little b because I used little b here, right? So that's just the region that you're minimizing. It just means a bulk region that you're minimizing here. Okay, so what is the goal of this paper? Well, basically the aim is going to be to generalize Daniel's theorem to allow these sort of variable entanglement wedges, where different states have different entanglement wedges. But to do that, we're going to have to sort of add quite a lot to it because it's allowing much more general things. It's basically allowing anything that actually happens in gravity, not just these very simple cases where little b is fixed. So we're going to end up with sort of a richer class of quantum error correcting codes, more general class of codes. And we're also going to end up with richer sort of emergent geometries. And that's because there's going to be more surfaces getting involved, right? There's not just the one little b anymore. There's all these different ones. And so we're going to have a lot of different surfaces, all of which are going to need to have different areas. So there's two sort of big things that we need to do before we can even get to a statement of this theorem. In fact, by the time I reach a statement of this theorem, it will basically be the end of the talk. I'll briefly say something about how you prove it, but really I just want to motivate the theorem. The first one is going to be to just define areas for arbitrary regions little b. So Daniel gave a definition of area, but his one only worked for the little b that had complementary recovery in his sense. And so we need to define something that's much more general than that. And the second thing is to make a precise definition of what it means for big B to encode little b when different states have different regions being encoded. And it's not as simple as just there's some fixed region that for any states you can recover that region. Different states have different things. Okay, and so this is going to involve something called state-specific reconstruction. State-dependent reconstruction basically means the same thing. Basically, we're going to have to allow different reconstructions to be used for different states. So you have to know what state you're trying to learn about before you can learn about it, which slightly seems paradoxical, but hopefully will make more sense later. Okay. And in fact, it turns out that sort of, the Harlow style definition of reconstruction, which basically means that, if I know the state here, I can find the state here without knowing anything about it, will only be possible if the region we're trying to reconstruct, the bulk operator we're trying to reconstruct, is in little b for all states in the code space. For pure and mixed states in the code space, like absolutely everything. That's the only time you can get it. Yep.
Is one way to think about this as sort of Harlow doesn't think about back reaction of sort of matter onto the geometry in a way?
It's similar to that, but we can still think about a code subspace where all the states have the same geometry. It's more like, it's more like back reaction. We have this min over area plus area of B plus S of B. And Harlow doesn't think about how this changes the B that minimizes it, right? He's sort of taking it, he's sort of taking it outside the minimization and assuming that it doesn't affect it.
Exactly. That's the sense I meant. It's not that direction.
Yeah, so he's in a sense, Harlow is dealing with sort of Fogman, Lukovitz, Maldacena, where they knew about this bulk entropy correction, but they hadn't put it inside the minimization yet. They were still just minimizing over area and then adding this as an extra correction once you'd found the relevant region middle. Yep.
So you're basically generalizing the standard, like in standard quantum error correcting codes, you want the recovery to be the same for all the states. Right?
Yes. So we will have to generalize the usual notion of quantum error correction in order to get this. Yeah. Yep.
On the previous slide, when you purified the state,
yeah,
minimized over B. Yes. So when you, I mean, the choice of purification isn't unique. What you expect, the geometry of everything will stay the same, even though you.
Yeah. So the only way the purification appears is in this term here and in this term here, which again has a typo. And those entropies don't care what purification you use, right? All purifications are equivalent up to a unitary, and applying some unitary to this system will not change the entropy.
What you're minimizing B. So the only term that's affected is the not the geometric term. It's
exactly. It's This B tilde is still just regions of the bulk, so that doesn't involve the purification at all. It's just there's this extra R that appears.
Is complementary recovery in some sense implying anything hyperbolic about the geometry, or?
Ooh, that's a good question. Quite possibly. I don't know. It's not obvious to me that it would be true in like flat space or something like that. It does seem like to the extent that you only have a CFT if you have ADS, then I think you probably only have complementary recovery if you have ADS. So yeah. Quite possibly. Okay, let me start on these two tasks then. Let's start with number one, because that's pretty simple. Because we have a beautiful definition of area that was come up with by my collaborator, Sakers, so I can say all the nice things I like about it. How wonderful it is. Okay, sorry. Before that, I should define the setup. Okay, so it's basically the same thing I drew here. We have some isometry V. The maps are logical bulk state to boundary state. But now I'm wanting to have a lot of different little subsystems in the bulk, right? So the bulk, I want to have some complicated geometry. So each of these little subsystems represents a different little local region of the bulk, okay? And then the full bulk Hilbert space is just a tensor product of all those subsystems. So B1 tends to be B2, tends to be B3, so on, distributed around the bulk. They get mapped via some isometry that represents sort of bulk to boundary mapping those states into CFT states. And then we're splitting the CFT into a region big B and a region big B bar. Yep.
So everything is still sort of order LADS size, all of these little b's I should imagine, or?
I think you could probably make them, I think this should be large compared to the Planck size, but I don't think they need to be ADS guys or larger. I think that they could be arbitrarily small. Yeah, compared to the ADS guy. You just need the bulk to be well described by a semi-classical effective field theory. That's fine as long as it's larger than Planck scale. Yeah. Like QAS prescription, rear tachynuclei are valid at scales well below the ADS scale. So this should be true. Okay, so we have all these subsystems, little b1 to little bn. I'm going to use bold b, little b to just represent an arbitrary subset. So say little b1, little b3, little b5, for example. That might be some, so that would correspond to some little region of the bulk that just contains those three and nothing else. Okay, so now we want to define areas. And as I say, this is a really nice definition. It's entirely due to Chris. So there is a special state called the Troy-Jamelkowski state that if you're familiar with quantum information, you're familiar with, but otherwise I'll take a moment to define it. It's very simple. What we do is we take a product of maximally entangled states on little b1 to little bi, tensored with some reference system isomorphic to it that I call little r. Okay, so we have a maximally entangled state on little b1, little r1, tensored with a maximally entangled state on little b2, little r2, and so on. Okay, so that's the state here. Then we take all our little B systems and we plug them into that isometry V. Okay, so now we have a state on big B bar, and all these little reference systems, little r1 to little r. Then just define the area of some set of little b's, say little b1, little b3, little b5, to be the entropy in this Chor-Jamalkowski state of big B together with the corresponding set of little r's. So in this case, it'd be little r1, little r3, and little r5. Okay, so this gives us an entropy for an area associated to any of the any subset of the bulk, any subregion of the bulk. And it's an area that depends only on V, okay, because the Chor-Jamalkowski state is defined by V, and also on this big B, okay? And you might say, why should the entropy of a bulk region depend, the area of a bulk region depend on big B? It's because it's the area homologous to big B, right? When we calculate these generalized entropies, we're always using areas of some region homologous to some boundary region. That's where the dependence on big B comes in. Okay. Any questions about that as a definition?
Well, I guess you could use the V dependence to take off the big B dependence and write in terms of little b, because
yeah, you can think of, yeah, you could have, sure. I'm just saying if you keep V fixed but then change B, then it changes. But yeah, if you change V, then you can think, also just think of that as a different V. Yeah, so it's really just determined by the code. Okay, so it is worth commenting on this is our claimed definition of area. If we plug in this definition into like actual ADS CFT, does it give the right answer? And the answer is not always. So if I have ADS CFT and I had some super wiggly state region like this, then this answer would not, this area that I've just defined would not necessarily actually be equal to the geometric area of this region. Okay. However, what is true is that if we have some surface that for any state in the code space, for any bulk state we're considering, this region can actually be quantum minimal. It can actually minimize this formula here. Then this area we've just defined will always be equal to the actual geometric area in gravity. But really wiggly regions like this one that aren't ever quantum minimal, then this definition lower bounds the actual geometric area. Okay? But if we're only really interested in how this formula works, then making an area bigger that is already so big that that surface never actually is minimal for any state in your code space, you haven't really changed that prescription at all. Okay, so we say that it gives a functionally unique quantum minimal surface prescription, in that changing this area to make it bigger for surfaces that aren't minimal anyway doesn't really matter. Yeah.
How do you characterize surfaces that can never be quantum minimal?
So I just mean if we can just look at all states psi in the code space. Okay, if there's no state psi for which the minimization over little b gives that answer, then I'd say that region is never quantum minimal.
Sounds like a hard thing to check.
Oh, it's a hard thing to check, yeah. But you sort of don't need to check, right? Like the point is that your definition was right. If you ever find that area actually matters, if you ever say do a computation and you find that thing matters, then you know that the definition is right for it. So if you ever find yourself caring about that surface, then you'll have the right definition for it. Does that make sense? Like the theorem is only going to involve this quantum minimal surface description here. So it's sort of, it's the right definition of area for our purposes. If you cared about areas in other contexts, you might want some other definition. Okay. So now, so that's sort of task one done. Task two is how this gets related to quantum error correction. This is maybe a little bit more annoying for people from a high energy background, because it's a very, very quantum information-y sort of definition. So I'm just going to take a few stages to sort of get there. So don't try to read all the details of any of these theorems. Yeah, well, that's because I just copied and pasted some theorems. Do not try to read the whole theorem. This is not meant to be read. This is just to reference the important parts of it. So even with ordinary quantum error correction, there's a load of different definitions that are actually equivalent. And sort of one that you see in a first course on quantum information is that you have this isometry V, and then you throw away big B bar, you're just left with access to some subsystem big B, but then there's another isometry, WB, that gets you back the original state. So you can sort of invert that channel of applying the isometry B and then throwing away some subsystem. Okay, so that's the sort of definition that's probably most familiar to people. It's actually not a practical or operational definition, even in like quantum computing or something, because you know, the moment you do this WB and like undo your encoding and get back to your original state, then you no longer have any quantum error correction. So then if an error happens, you're screwed. So you never actually do that in practice. In practice, what you do is you always work with the encoded space, the encoded state, and you try to simulate doing things on the logical state by doing stuff to the encoded state. So in particular, these two definitions are both basically saying that any measurement on your state in the code space, on your logical state, can be done by using a measurement just on big B. Okay, so we don't have to don't have to know anything about big B bar. We can just do a measurement on big B that will do the thing we want it to do. Okay, so that's one thing you might want to be able to do physically. There's another thing, of course, which is to apply some algorithm to your logical state. Right, so we could want to apply some U code to our state ket psi, and if we can do quantum error correction, we can just apply some U big B to the system B without having any access to B bar that's been lost to the environment or whatever, and we can still implement that unitary evolution. Okay, so these are both things you in practice would want to do, but if you can do one, you can do the other. All these four definitions are all equivalent. Okay, so that's just ordinary quantum error correction. As I said a while ago, there's a very natural generalization of it, where rather than being able to reconstruct the entirety of your code space, you only have to be able to reconstruct a subsystem of it. It's a little b. So that's in fact what Daniel was working with. It's called subsystem quantum error correction. Okay, so again, four equivalent definitions, they're all almost exactly the same as the one before. Okay, so now our WB, rather than getting back the entire logical state in the code space, it just gets back our reduced state on region little b, the subsystem that we're meant to be able to reconstruct. Okay, similarly, rather than being able to simulate all measurements on the code space, we can only simulate measurements on the subsystem little b. And of course, rather than being able to simulate any unitary evolution on the code space, we can only simulate unitaries that act on the subsystem little b. Okay, so again, all of these things equivalent to one another. So that's sort of one direction of how you can generalize ordinary quantum error correction. There's an orthogonal direction you can generalize it, which is to have this notion of things being state specific. Okay, so this sometimes called 0-bit codes. That was a term Patrick and I introduced another paper 2017. Don't worry about all these definitions, just to show you that there are again a load of equivalent ways to think about it. The nicest way for our purposes will be something very similar to condition 4 in the previous slides. So again, we have some U code acting on psi that we want to simulate. We want to simulate it with a U big B. But now we're only going to be able to do it if we know what the state psi is. So we're allowed to choose our U big B in a way that depends on the state psi, that is specific to the state psi, in order to be able to implement our U code. Yep.
Why is there an error threshold here and not on the
previous?
Yeah,
that's a great question. The reason is it turns out that if I stick these errors to 0, this actually ends up being equivalent to my first definition of quantum error correction. It's only when you add in a little bit of noise that it actually helps to have your U big B depend on the state psi. But once you add in a little bit of noise, it helps an awful lot. So for example, if I have 1 million qubits in my code space, then with ordinary error correction, I need at least 1 million qubits in big B to be able to encode them. In this, I actually only need roughly 500,000 qubits. So you can have an awful lot of noise and still be able to do this, it turns out. if you've encoded it in a sensible way. Okay, so everyone clear on like what I mean by this U big B is allowed to depend on psi, but it's chosen after we choose psi. Yep.
For this noise bound that you have here, like, are these specifically dependent on the state also, or how are these determined?
These will be true for all states. These different epsilons are all related to one another by some messy stuff here that I've written at the bottom. So it's not exactly the same epsilon that appears in each one. But if you know this is true for some epsilon, then this one is, this epsilon is bounded, all the other epsilons are bounded. But don't worry about the epsilons. I'm just putting it in so that it's not a total lie of a theorem. Okay.
So the reason you're introducing this epsilon is what? It's to allow yourself a wider choices of U big B.
Yeah.
To do the encode.
Yeah, it's just easier to like approximate quantum error correction is easier than exact quantum error correction because you allow you allow yourself a bit of noise in the state you get back. But in particular, this definition, the state-specific definition, gets like a lot easier. And so if you didn't have the noise, they're like equally hard, state-specific and not state-specific. If you allow a little noise, then state-specific gets way easier than not state-specific. And the reason,
but there is a state independent U big B no matter what, right? Because that was what your previous theorem.
no, because in this theorem there is no state independent. Well, I mean it depends on the code, right? These are sets of equivalent.
So what's different between the previous slide and this slide?
The different, more general classes of B. So there will be many more V's that will satisfy these sets of conditions than there will be V's that satisfied the previous slide sets of conditions. Okay. So yeah, there's a lot more codes that will have these properties than have previous. Okay. So in holography, we sort of have both the previous two slides. We have the notion of some subsystems are encoded in one thing, some subsystems are encoded in another. It's not just like everything goes to the same place. But we also have this notion of things being state specific that you need to, you can only sort of implement reconstruction if you know what the state is.
I think I'm still missing the logic. So if we go back to n equals 4 Yang mills.
Yep.
So before I listened to this talk, I would have said, okay, there is some embedding of supergravity into n equals 4 Yang mills.
Yep.
And so you're saying that actually there are many embeddings of supergravity in n equals 4 Yang mills?
No, sorry. N equals 4 super Yang mills will not be an example of a quantum error correcting code of the form in the previous slide. Certainly will not be an exact example. If you treat it as an embedding of just like one qubit in the middle of the bulk into the boundary, then it will be an approximate example of the original quantum error correction thing. Okay, but for larger code spaces where we have more supergravity states in our code space, then it will not even be an example of that. And but it will still be an example. It will still satisfy the conditions of the theorem that I'm going to get to, right? So it will, the entanglement wedge reconstruction will still be possible, but it will both only be for certain subsystems, namely the ones in the entanglement wedge, and it will be state specific because the entanglement wedge will be different for different states.
So you're saying that in n equals 4 Yang mills, there is no V corresponding to the previous transparency?
Yeah, I mean, what V you have depends on your code space, and that's sort of a choice, right? I could just consider two states, one with an electron sitting in the middle and spin up, one with electrons sitting and spin down.
But let's take, say, all states that you could realize within supergravity up to some energy.
Yeah, unless your energy is really low, so you only have two states or something,
yeah.
then there will not be an example of actually any of the, that will not satisfy any of the things I've said so far, but it will satisfy the one I'm going to get to. Okay, good. Great. So yeah, so for those V's, we're going to need both subsystem codes and we're going to need things to be state specific. So how do we sort of combine these two generalizations? That actually hadn't been done before this paper in a sort of correct way, I think. But there's a sort of obvious first guess. Well, it's sort of obvious we should be using this condition 4 and the previous condition 4 because that's the only condition that appeared in both the generalizations, right? They're in very similar form in both generalizations. So we're going to do that. But then you have a question of, okay, which unitaries should be reconstructible on big B? Okay, so sort of naive first guess is that, you know, we have some set of subsystems that'll be, and any unitary acting on that subsystem, those subsystems of bulk should be reconstructible on big B using a unitary, right? That's actually just not true in gravity. That would be very bad in gravity. Let me give you hopefully clear example of why that's the case. Let's say we have two black holes sitting in our bulk, and those black holes are very highly entangled with one another. Okay? I can set things up so that both black holes are in the entanglement wedge of big B, because if I sort of cut between the two of them, then I'd get a huge entropy from this black hole, right? But because they're entangled with one another, then if I have both, then they're both in the entanglement wedge. But now I could imagine applying a unitary just to that entanglement wedge that disentangles those two black holes from one another. So then we get a state like this, where the black holes are just in a product state, two product microstates. And now the quantum minimal surface does just go between the two of them, okay? Because you no longer get that huge entropy contribution. Entangled things. So that means that this unitary acting only within the entanglement wedge will have changed the entropy of big B. Clearly, we cannot do that with a unitary on big B on the CFT side. Okay, so it's just too strong from a gravity point of view to demand that all unitaries are reconstructible. What unitaries can you reconstruct? Well, you can reconstruct unitaries if they don't change the entanglement structure of the state, right? If it's leaving this black hole entangled with this black hole, that's not going to change the entanglement wedge. It's a well-defined, you should be able to do it on big B. Okay, what are those unitaries? Well, they're just product unitaries. They're products of, you know, we had all those subsystems B1 to N. They're products of unitary on all the unitary 1 on B1, unitary 2 on B3, unitary 3 on B5, or whatever. All within a set of B's that are within the entanglement wedge. Okay. Yep.
So isn't that saying that basically the Hamiltonian in the bulk doesn't entangle nearby degrees of freedom?
No, I think it's just about how information is encoded. You should not think of this as like time evolution. Like the boundary Hamiltonian couples big B and big B bar together, right? So it's just telling me about like what changes I can make just by looking at big B without having access to anything else. Okay, so the right definition is exactly this. So definition is that for any product unitary within our set of subsystems that lie in the entanglement wedge, we should be able to find an analogous corresponding unitary on big B that does the same thing, right? But that we not only need to know the unitary we want to implement, we also need to know the state set ket psi before we can implement this UB. Okay, so it's putting together, you know, we have sort of subsystem codes getting involved, we have state-specific stuff, and just to make everything work out, it turns out the sensible thing to do is to only have product unitaries have to obey this condition. Okay. We also want a notion of complementary recovery, complementary reconstruction. So that was important in Daniel's theorem, it's going to be important in this one. So we also want, if we have a unitary UB bar prime, and then we also want there to be a UB bar, right, that will reconstruct that one. So little b gets reconstructed by big B, little b bar by big B bar. In fact, for full generality, we want to allow mixed states. So we allow states that are sort of entangled with the reference system, that are purified with the reference system. But don't worry too much about that. You just want to forget about these big R and big R bar systems and just imagine there's only B and B bar. That's completely fine. This is just to make it as general as possible. These things are important for understanding mixed bulk states. We want to apply this to like islands and things like that, where we have these external reference systems, we need to include them. But again, just don't worry about it too much. Okay, so this is finally ready to state the theorem. Only 55 minutes since the talk. Okay, so we have two equivalent conditions. The first is exactly this notion of complementary recovery. That given a state psi, and two product unitaries, one on little b and one on little b bar, then we can find product unitaries on big B bar that will do the same thing, that act on a state in the same way. The second condition is exactly having holographic entropy prescription, area plus bulk entropy equals boundary entropy, with area defined as it was a few slides ago in terms of this Chor-Jankowski state. Yeah, exactly as I said. Okay, and it's not enough to just have this be true just for the state psi. That would sort of be too easy to satisfy. You could have that without having any information actually getting encoded. Instead, we want it to also be true for all states related to psi by a product. Okay, you might say, why shouldn't this just be true for all states? Turns out even in gravity, this formula is not true, even approximately for like all states in a general enough code space. There are states that are totally semi-classical, but for which this formula just really failed. So instead, it's just some class of like nice states for which is satisfied. So there's a paper by Chris and I from 2020 that talks about that in detail. But don't worry about it too much. Just note that we aren't requiring all states to satisfy this. So something you might say is, okay, this formula still just is in terms of little b. There's no minimizing over anything here, right? It's the same as Harlow's theorem. We just have a little b where things are encoded, and that's the same little b that appears in this formula. Where's the minimization? Turns out the answer is that you get that essentially for free. So just by knowing either of these conditions being true, that is also necessarily the case that any other little b prime, say any other set of subsystems in the bulk, will have a larger generalized entropy than little b does. Okay, so this is always the smallest possible generalized. Okay, so any questions about that theorem? Because that's really, the main goal of the talk is to have you guys sort of have some appreciation for what this theorem is and what it tells us and why. Yeah. Yep.
So I guess one way to interpret the minimality would be, given such a recovery, there's like an optimal recovery map for
well, so no, generally only one little b will actually have recovery at all. Yeah. Right? Like the other things, just the recovery won't be possible. Yeah. I think the right way to think about it is that there's just, the way information flows, it like naturally always has to minimize this thing. This minimality condition follows from some strong subadditivity stuff and some arguments based on that. So that's where it's coming from, but it's a technical proof that I'm not going to go into. But I think you should think of it as a statement along those lines that sort of everything has to be larger because that's how information flows around. Yeah.
I guess I'm a little confused that on the left-hand side usually, so when I previously had the minimization over b, yeah, it didn't appear on the left-hand side of the equation. Like here you have this S of BR, who seems to also have to specify that.
Sorry, the big B? Wait.
The little b in the state, basically.
Yeah, so I'm saying this formula could be replaced by minimizing over all b. Okay, and the reason we do that, know that, is whenever this is true, or whenever this is true, then this will also be true. So this little b is always the minimal middle. One thing that isn't true is that if I just have a general code, then this entropy will not be equal to the minimal little b necessarily, right? Because there's a lot of codes out there, a lot of isometries V out there that do not satisfy any conditions like quantum minimal surface prescription. So you can't get from this condition to these first two conditions. But you do, if you have these first two conditions, then you do always have this minimality condition, that all other little b's have a larger generalized entropy. Does that make sense? Okay, so I just want to give a very brief flavor of how the actual proof of this theorem works. I'm not going to go through all the different steps, but give you a sense of the sort of tricks involved, how this area, which is some entropy in some Chor-Jankowski state, gets related to boundary entropies and so on. So it turns out the heart of this proof is a sort of neat little trick with some Haar integrals. So what you can do, you can define an isometry W acting on some subsystem, little bi, where what it does is it applies a Haar random unitary to little bi, and then stores that Haar random unitary in some auxiliary system. Okay, so this is just a label, this is like a position basis for some square integral functions on the unitary group. and it just saves, remembers which unitary it applies all those things in coherent superposition. Okay, so that's an isometry. You can look at what this thing does. So let's say we forgot about this auxiliary system. Now we've just applied a totally random unitary to that subsystem bi. That will just leave it in the maximally mixed state. Okay, it deletes all the information from little bi. So what does this thing do on the full system, including this auxiliary reference system? Well, little bi has to end up maximally entangled with something in your auxiliary system. Indeed, it does. Called that little ri, the subsystem it gets maximally entangled with. It turns out that the sort of part of psi that was in this little bi just gets copied across into the auxiliary reference system as well. Some other subsystem I call little ai. Okay, so what this thing does is it like takes little bi out of the state in little bi, out of little bi, swaps it out for half of the maximally entangled state. As a result, if condition 1 is true, then we can define an isometry that just acts on big B on the boundary. And what this does is it's just an integral over product unitaries stored in auxiliary reference system, tensored with the reconstruction on big B. Okay, so what this does is it uses this ability to do reconstruction to extract the bulk state out of little b into some auxiliary reference system and swap in half of a maximally entangled state. Graphically, that looks something like this. So we have our operator acting on big B, takes the part of the bulk that was in big B out of the bulk into some auxiliary system and swaps in something maximally entangled with a reference system. Okay. Now we can do the same thing on the other side, on the big B bar side. That swaps out the part of the bulk that was in big B bar, swaps it into an auxiliary system, swaps in half of maximally entangled state. But now we're left with just the original bulk state, which has now been totally extracted out of the bulk and is just sitting in some auxiliary system, like non-holographic system, tensored with our original bulk in the Chor-Jamalkowski state, maximally entangled with this reference system. Okay, should be getting a hint of now how we're going to relate sort of the boundary entropies to this area term that involve the Chor-Jamalkowski state. So just to very explicitly show the proof of how you get from condition 1 to condition 2, just an example. So we're wanting to compute the entropy of big B in the state B applied to a bulk state ket psi. We then apply the unitaries WB, WB bar to that state. That does not change the entropy because they're just isometries. Okay. But then after applying that state, we're just left with the product state. We're left with the product state, the bulk outside, it's been extracted out of the bulk, and the original bulk state is just sitting in an auxiliary system, tensored with the Chor-Jamalkowski state. So we just have the entropy is just the sum of these two terms. Chor-Jamalkowski plus the bulk state, but now it's the entropy of just ket psi, not V applied to ket psi, it's the bulk entropy. But of course, the Chor-Jamalkowski state is exactly a definition of area. Okay, so that's how we get from this boundary entropy to area plus bulk entropy. Okay, so that's really all I'm going to say. I'm not going to go through all the other steps of the proofs. They involve similar tricks of using these W little b's and doing stuff with them, and various entropy equalities and so on. But I'm just gonna end with a couple of final comments. Firstly, let me sort of review for anyone who's been asleep for the last 45 minutes or got completely lost 2 slides in, what the sort of big picture, the big idea of this talk was. We're showing that there's equivalence between having some sort of entanglement wedge reconstruction, having the bulk encoded in the boundary, and having some holographic entropy prescription that a formula that the sort of area plus bulk entropy with boundary entropy goes well beyond the sort of baby version of it that Harlow showed, where there was a fixed region and that got encoded in the boundary that didn't bend on a bulk state. Okay, and this was obviously important for things like islands, for other situations where you have a large amount of bulk entropy, and that can change the entanglement wedge of regions. What this means is that any complementary state-specific quantum error correction code, it's really a very, that sounds like some weird, wacky thing that no one cares about. I didn't talk about this, but basically any of the previous classes of quantum error correcting codes, anything you could call a quantum error correcting code, at least with the notion of complementary recovery, will actually be a version of this. It's a very, very general notion of what something means to be a quantum error correcting code. Has an associated sort of emergent bulk geometry where you have areas associated in each sort of logical subsystem, and as those areas give a functionally unique quantum minimal surface description. So I didn't talk about this much, but our theorem is actually robust to errors. There's an approximate version of it we proved in the paper. The proof is just more horrible. The statement of the theorem is more horrible, and so on. And this is obviously very important because in gravity, there are always non-perturbative corrections that will give you errors when you try to reconstruct things. And also, it's not clear, I think, any interesting examples of these codes, the sort of non-trivial, will almost certainly be approximate ones. I'm not aware of any non-trivial exact codes. Actually, there's something I didn't talk at all, but is very exciting, which is that we can allow this map V to not even be an isometry at all. We can allow it to be a general linear map. And this is exactly what you need to understand sort of the interior of a black hole at late times, where you sort of have more information inside the black hole than information actually describing the physical state of the black hole. Because the amount of entropy inside the black hole is bigger than the Bekenstein-Hawkian.
So in particular, everything that you said in this talk applies equally to fuzzballs and black holes.
Fuzzballs, I think you would work, well,
in the sense that you're just making some abstract statements about correcting
it
codes and
certainly
you don't
would
really
apply.
have any geometric.
So I think, I would have thought that a lot of fuzzballs people would want to say that there are only e to the s different fuzzballs.
Yes.
So I think to me, one of the most interesting things about this is that the semi-classical interiors of the black hole, there's this problem that it seems like you can have more of them than e to the s, right? But I think the island calculations and so on are saying that what's going on is that those just aren't more than e to the s independent states. It's actually, they're all really squeezed into some Hilbert space of size e to the s, and there's just non-perturbative tiny little overlaps between them that let them all fit in there. So in that case, your bulk to boundary map, you have these states that semi-classically are orthogonal. You have more than e to the s of them, but then they get mapped into e to the s different quantum gravity states. So that map sort of can't be an isometry because it has a larger input than it has output. So our code, our framework can deal with those. So in particular, there's an objection some people have made to the islands calculations from 2019, that those calculations are using a state, the sort of Hawking state, the semi-classical state, that has the wrong entropy, wrong properties, that does not obey the page curve, to then calculate the page curve and get the right answer from the wrong state. So this is going to be talked about more in some upcoming work with Chris and Netta and Daniel and other collaborators. But you can think of the way to understand why that's okay is that the physical state is not the Hawking state. The physical state is obeying the page curve, but the physical state represents an encoding of the Hawking state in this framework of like state-specific complementary reconstruction. And so if it represents an encoding of the Hawking state, then you can apply a quantum minimal surface prescription to the Hawking state, and it will give the right physical entropes. Okay, so that's the role the Hawking state plays, is that the actual real state that obeys the page curve represents an encoding of that non-physical state. So that's I guess all I have, which is good because been going quite a while. Any more questions? I guess, yeah.
So the question everybody always asks is, where did Hawking go wrong? Are you saying that it's in the over completeness of the basis he was working in?
I think that's nonsense.
Or is there also some of it that's at some point you had started introducing error tolerances into your reconstruction? So is there some wiggle room there as well?
I think there's a lot of answers you can give for where Hawking went wrong. One thing is he didn't include space-time wormholes in the path integral, right? One thing is, the interior states form an over-complete basis. But But I guess one lesson of this is that in some sense he wasn't as wrong as you might have seen, that the Hawking state plays a real physical role, that an encoding of it is the physical state has a relationship to it, right? It represents an encoding of it in this way. You know, in that sense, it's the same way that the semi-classical bulk state isn't like real because semi-classical physics isn't real, but the CFT state is an encoding of it, and that's the sense in which it's real, is that it gets encoded in the real microscopic physical state. So yeah, I don't know, maybe that lesson is that Hawking was more right than we were saying a year or two ago, or that his state at least plays more of a role than just being. It's not just a mathematical tool that you use in calculations, because the Euclidean path integral calculation says that you should do so when you take an analytic continuation. It's like it actually has some Hilbert space sort of significance, which is that the physical state encodes it in a certain sense. That's some words. Yeah.
But I mean, it sounds like from what we were just saying a minute ago, that there are large corrections to his calculation because there are an exponentially large number of exponentially small corrections to it.
I think that's also fair to say. Yeah. But I think the point is, even though that's like saying that this V is not close to an isometry, right? It's even though it's not close to an isometry, there's those large corrections at that level, then it still looks like an isometry if you don't look too closely. If you only ask about these simple unitaries, like product unitaries, then they get encoded as unitaries in the in the Hawking radiation. Like there's the Hawking state does not get completely destroyed, even though there's these non-perturbative corrections that at one level mean that the actual real state looks nothing like the Hawking state. It still has a relic, a sort of ghost of the Hawking state is still there in this encoding. But yeah, we put off all actual talking about that to this upcoming paper, so I don't want to like say too much about that now. Yeah, hopefully that paper will give our definitive version of the story for it. Yeah.
Okay, so you may have just answered this, but I want to be sure. So you said, so your theorem is robust to errors, and you said that's important because there are these non-perturbative corrections. But so when I think of an error, I think of a perturbative error, right? Because if you just in any sort of error correction problem, if you make a large enough error, there's no way to correct it. So what exactly do you mean by errors here, if not something else?
Sorry. By non-perturbative, I mean smaller than perturbative. I mean non-perturbative in the sense that it doesn't appear, it's too small to appear in a perturbative expansion in G.
Oh.
So something that looks like e to the minus order 1 in G. That's the sort of errors that we're talking about. Things that come from other saddle points in the path integral, that sort of thing, will give these sort of errors that, yeah. So to all orders in perturbation theory, you can actually make it exact with sufficient work. Yeah.
So when I think about expanding the entanglement entropy of the boundary in terms of 1/n correction, so I have the area, then I have the order n to the 0 piece, which is the bulk entropy, but there'd also be all these subleading corrections.
Yeah, you mean like higher curvature corrections and stuff. Higher curvature corrections I was implicitly including in the area.
Well, 1/n corrections.
Yeah, you meaning separate from higher curvature corrections? I think so. There's a paper
Curvature would be like lambda corrections.
Sorry?
Those would be like Tooft corrections.
Yeah.
That's only a subset of the 1/n correction.
Yeah. So
Okay,
there's a paper by Dong and Lukowitz from about 2018 and so on, arguing that basically this formula should be exact to all, well, with this replaced by some appropriate local functional, call this like LA on like TB on the boundary of B, So that including like higher curvature corrections and anything else that's a local function of the geometry at the edge of the region, that this should be exact to all orders of perturbation theory. So I don't think there's like corrections to this term at a perturbative level. Yeah. Like, yeah. Certainly when I'm writing area, I really don't mean area. I mean the thing you get, but you think you can argue that it all comes down to like geometry and like there'll be corrections from back reactions to geometry from the matter and so on at higher orders and stuff like that. But it's sort of the essential form of this, I think, is true to all orders of perturbation. So yeah. Yeah. Certainly in well, I was going to say, yeah, in very simple things like say the West Coast replicable wormholes model, you can explicitly evaluate the source of the errors and that these non-perturbative corrections, and that's consistent with things you'd expect. But there you sort of don't really have any perturbative corrections. So you don't have much in the way of interesting perturbative corrections. So that's maybe not a good example. But I think the interesting corrections, I think, will be non-perturbative corrections.
Because just from the like Lukowitz model setup, but you'd imagine that there's this whole.
Yeah, but I
you're
think
just getting
that's
the first
it's
correction,
all
right?
just like
You're saying it somehow just all gets encoded in this LA.
well, because if you looked at Rainy entropies, then I think you get more. But you're only going to get things that are first order in n-1.
Oh, that's true.
Right? Because you're really taking a derivative at n equals 1. So that, yeah, I think a lot of stuff gets killed off by that. Yeah, basically, this area term becomes whatever you get from the conical singularity, from back reaction, you get the conical singularity. But then, yeah, the stuff away from the conical singularity, I think, just always gives you this. There's nothing else. More questions? Have I exhausted everyone? Sorry?
I was gonna say lots, but I think we should release everybody else.
Yeah, sounds good.
What's your time? Jeff, again? Yeah.
I need to reference and take them. Easiest way to do this thing.
Right now? You guys sound taking Jeff there. I'm gonna go grab some stuff for you. I'll meet you there.